So today we're going to look at question 19 from chapter 4. And I have it here. Pull it up. I've got the question, and then I'm recording, so I'll post this video so that you can take a look at it later, or that. And so this question, I don't think in the book they really address it directly, but you'll see if you watch the video that goes with this, it's called Bayes' theorem. They use a lot of formulas and such. We're going to do it with just a tree diagram. So we won't call it anything official, but we'll do it very visually, okay? And where this really comes in is we're going to look at a problem with a virus, and it comes in with medical issues such as cancer and such, and testing. And we're going to see if you have it, what's the probability that your test is accurate, and you don't have it, is it accurate? So because there's two things we worry about with testing, right? I mean, if you get it and it's accurate, that's great. But false positive, what would a false positive be? It says you have it, but you don't. Now, that makes you feel real stressed, but you'll probably go get a second test, and maybe the second test will be accurate, or hopefully they don't push you into a surgery that you don't need. Occasionally that happens, but a false positive, not a good thing, but what's the more dangerous thing? A false negative, because it says you don't have it when you do, and you should be getting probably treatment early on, and it's not caught for maybe till later on, till you get really bad symptoms. So, and we want to see what's the probability of those things happening. So we're going to use a tree diagram. I've kind of got it set up here, but we've got a certain virus, and it's known at this point to affect about every 1 in 300 people. Where does that information come from? How do they know it affects 1 in every 300? Medical data of people coming in. Is it accurate? Maybe, maybe not. So this is the thing, is a lot of our calculations based on something that we don't necessarily know, because we don't know till you test everybody, and the test isn't 100% accurate. So this is oftentimes a figure that is sort of pulled out of the air. They do the best they can, but this number could be wrong, okay? So you could play with it. What if it was really 1 in 200 people? How is that different? Okay, but that is something that we're going to use. 1 in every 300 people. Okay, a test is used to detect the virus in a person. Is in a virus in a person is positive 85% of the time if the person has the virus. What kind of a probability is that? Remember, percentages are probability. What kind of probability is that? Kind of done two probabilities, right? Regular probability and conditional probability. That's a conditional probability. Okay, so it's only 85% if the person actually has the virus. Okay. This is something we don't know, right? That's why we're testing. It's 10%, so it's positive 10% of the time if the person does not have it. Okay, so those are the probabilities we're given. Let's see if we can set this up. Okay, they ask us to let A be the event, the person is infected, B be the event, the person tests positive. So notice how those two are two different things. So we've got a virus going around. Event A is that they are infected. Event B is, or A not, is that they are not infected. Make sense? What are the probabilities here? If 1 in every 300 people is infected, would it make sense to say that the probability of getting infected is 1 out of 300? Hopefully it does, because that's the counting, right? 1 person out of 300. So how many people are not infected? 299 out of 300. Awesome. So you guys see. The thing is these numbers don't look very well when you turn them to decimals because this one's really small and this one's almost 1, but we'll see that. Then the next level is the testing. A, if they're infected, what's the probability of getting a positive test? Well, that came from up here. If it is positive 85% of the time if the person has the virus. They're infected. This is going to be positive 85% of the time, so we'll do that as a 0.85. They would be negative. Well, if you're positive 85% of the time, how many percent of the tests would be negative? 15. And this is always going to add to 100 because if an affected person is tested, they're either positive or negative. I guess there's some tests that can come back inconclusive, but usually they list those as negative and test them again. But we'll just try to keep this simple. It's already complex enough, right? So if they're not infected, what do we know? 10% of the time if the person does not have the virus, they still have a positive. So there's our 10%. And so then they get a negative 90% of the time. Okay, so not infected but positive, this is a false positive. Infected but negative, that's a false negative. Okay, so those are kind of the ones we're sort of interested in. But this is the setup, so it does suggest making a tree diagram, which is, in my experience, much easier to take a look at than trying to follow Bayes' formula, which if you want to, you can take a click on the video that is linked in the homework, and the guy walks you through it, but I find it confusing. Okay, so here's the question. Find the probability that a person has the virus given they have tested positive. Okay, so I'm pulling up our tree diagram. We want that the person what is it? Probably that the person has the virus, so that they're over here, they're infected, given that they have tested positive. So what we know is that they've tested positive. So they're right here or right here. The way a tree diagram works with conditional probabilities is the total probability. Remember we did this with that guy that was getting dressed, the 2 genes and the 3. It's the multiplication principle. So to go down any pathway, we simply take the, I think I'm already read. We take the probabilities and multiply them. So it's 1/3. So starting with the virus, we've got 1 out of 300, and then this positive branch is going to be 0.85. So we'll multiply that right here. And when you go to do this in the homework, your numbers may be different, either the percentages or the virus. So you'll just have to follow along with the, it's pretty much the same thing. 0.85. So we will just calculate 1 divided by 300 times 0.85. And that gives us 0.00283. And what you're going to need to do is carry this out to 5 decimal places, because if you don't, when you go to do your final answer, you'll get a rounding error. Okay, so that's the thing with these, you really need the long ones. The other thing that could happen is they'd be positive here, so the way we get that is we take the pathway, 299 over 300 times 10%. So 299 over 300 times 10%. Okay, and I'll go ahead and do that. 299 divided by 300 times 10%, 0.1. And we get, it's not as big, 0.099666666. So if I go 1, 2, 3, 4, I do the 5 decimal places, we'll round that last one to 7. Okay. Now, what do we know in this question? They have tested positive. Nothing else exists. So this is 100%, the two of these together. This is our world. So now they're asking, what's the probability that the person has the virus? So that's this one here. And the probability that they have the virus and testing positive is 0.00283. Out of, so this is kind of accounting, that's the event that they have the virus after testing positive, or the, and then what is the total things that could happen? 0.00283 plus 0.09967. So you'll take this, and you'll see this is where Bayes' theorem comes in. It's just saying basically one of us is in the top. You'll always see it in the bottom. The bottom is at least two things. Now with Bayes' theorem, this could be used if there was 3 different things that happened or 4 different things, which often does happen in these type of deals. It becomes even more complicated, and it's difficult to use a tree diagram if there's 3 or 4. But with only 2 items, it's not so, the tree diagram is much easier than trying to sort through all the symbols in Bayes' theorem. So what we get is 0.00283 divided by parentheses 0.00283 plus 0.09967 in the parentheses. I come up with 0.0276. So as a percentage, multiply it by 100, which moves the decimal over 2 places, there is a 2.76% chance that a person who is tested positive actually is infected. Means a lot of people over here are getting a positive test, right? 10% of them, and 10% of 299 is almost 30 people, right? 30 people are getting a positive test, but they're not infected. Since this is only 1 in 300, again, doesn't happen very often. So only 3% of the people who test positive actually have the virus, but we got to do it, right? I won't walk through the next one, but the next one is the same thing, but they want to find the probability that the person does not have the virus, given that they have that they test negative. And so if you want to walk through this, we'll just set it up, right? They have the virus, they've tested negative in both cases. So we're coming here and here. And so the pathways are going to take this one, and this pathway is going to include these here. So you're going to multiply these two, you're going to multiply these two, and which is the one we're looking that they do not have the virus. So we're interested in that this happened. Okay. So just again, briefly, 1 over 300 times 0.15, 299 over 300 times 0.90. You'll get these two numbers. We'll call this the square. Call this one triangle, whatever those numbers are. And in the end, you're going to have whatever the triangle is divided by the square plus the triangle. So it's, once you do it a few times, you go, okay, it's not so bad. But it's setting it up as long as we only have 2 things happening, and then positive or negative. If you got 3 things, it can get a little dicey. Okay. But that's where maybe the formula is helpful, and you'll see that in a more advanced statistics class if you take a junior level or a graduate level statistics class, you'll see Bayes' formula in all its beauty. But remember, it all comes back to this tree diagram, and that's the tree diagram is how you understand it. Okay, does that help? Maybe. And again, I know you could get full credit on the homework without doing this one because it's only one question, but this will be on the test. So there'll be a practice test with it as well, because I think it's that valuable. It tests on several different things, on conditional probability, tree diagrams, multiplication. So I can test you on about 4 different things at the same time with this one question. Any questions? Okay, so please make good progress. Again, I know a number of you already are, but just keep making that progress, because I don't give late penalties, because late penalties only work if they scare you enough to get it done on time. If you don't get it done on time, then you get a double penalty, you lose points, and you have to work harder. I figure you have a big pile of work to do, that's enough of a penalty. So I don't put additional score penalties on it, but try not to get there, okay?